Hello students, this is Professor Chalai, and in this video we're going to look at multiple bonds and electron delocalization. As always, you can follow along with our Chapter 8 workbook. By the end of this video, you should be able to relate sigma and pi bonds to hybrid orbitals, and also relate pi bonds to electron delocalization. Let's get started. In this section, we're going to combine things that we learned a couple videos ago when we talked about valence bond theory, and also what we learned in our very last video when we talked about hybrid atomic orbitals. So in valence bond theory, we talked about how bonds are formed when atomic orbitals overlap. So you have two atoms right next to each other, they have their orbitals, they will overlap, and the types of bonds that they form, whether it's sigma or pi, depends on the type of overlaps from the atomic orbitals that they have. So if we have two s orbitals, they overlap to form a sigma bond. If you have an s or a p orbital, they also overlap to form a sigma bond. Or if you have two p orbitals, they will also overlap to form a sigma bond if it's the first time that they're doing so. For pi bonds, right, we have overlap of p orbitals when it's not the first time that they're overlapping. So that's what we talked about for valence bond theory and overlap of atomic orbitals to form bonds. However, in our very last video, we talked about this idea of hybrid atomic orbitals, where s and p and sometimes even d orbitals can team up before they form bonds. So how can we use this idea of hybrid orbitals and also atomic orbital overlap together to figure out the kinds of bonds that are formed between atoms? Well, let's look at it. Before I get into that though, I would like you to draw the structure of ethene, that's C2H4, the Lewis structure of ethene, which you should have a lot of practice drawing Lewis structure right now. So pause the video and do that, and then you can unpause and we'll continue. So ethene has this structure. So this is the Lewis structure of ethene. Now, what is the hybridization of the carbon atoms around this molecule? Well, let's look at it. It has 1, 2, 3 sets of bond or electron groups, if you will. So we know that it must be then sp2 hybridized. I think I spelled that correctly. Okay. And we learned from valence bond theory that for sigma and pi bonds, let's use green, that all of the single bonds are going to be sigma bonds, right? Sigma, also a sigma bond. The first of the double bond would be sigma, the second would be a pi. So we learned that. We know that there are sigma and pi bonds, and so between the two carbon atoms, there's one sigma and one pi bond between the two carbon atoms. That answers the question. But how does the idea of sp2 hybridization relate to sigma and pi bonds? Earlier, we talked about how sigma and pi bonds are related to overlap between S and S, or S and P or P and P atomic orbitals. They don't mention anything about hybrid orbitals, like sp2 hybridized orbitals. Well, let's look at the electronic structure of carbon. Right, carbon we know has a 2s orbital that's filled, and then a 2 p orbitals that are, well, there's 2 electrons in here because carbon has 4 valence electrons. Because we know that this molecule is sp2 hybridized, what that means is before it bonds, as you would imagine, one of the s and 2 of the p orbitals hybridize to form 3 new orbitals with labels sp2, right? 1s and 2 p orbitals hybridize, and then that means that there's one leftover p orbital here that's not hybridized. So let me put my electrons in here. 1, 2, 3, 4. You might be wondering where I should put them. I'll just put them here because technically this carbon has 4 bonds. 1, 2, 3, 4. So we need 4 electrons that are unpaired that needs to overlap to form bonds. The other carbon the other carbon here would also do the same thing, right? It has an sp3 hybridization, and so it'll have these 4 orbitals ready for bonding. Now, let's see how it actually bonds. When these sp2 orbitals overlap with other sp2 orbitals or s orbitals, because so it'll overlap with other sp2 orbitals from the second carbon or other s orbitals from the hydrogens, they will form sigma bonds. However, as we learned earlier, when the p orbitals overlap, so there'll be one p orbital from the left carbon, one from the right carbon, when they overlap, they'll give us the pi bonds. And so that's how we can get sigma bonds and pi bonds from hybridized orbitals. Our sp1, 2, or 3 hybridization, when they overlap, they'll give us sigma bonds. And if we have other p orbitals that are still left over, they'll give us pi bonds. Okay, let's look at number 5. If you haven't yet, please draw the Lewis structure of SO2 on your own. Then you can unpause and we'll do it together. Okay, the Lewis structure for SO2, I'll draw it like this. We have 6 valence electrons from sulfur, 6 from the oxygen. There's 2 of them. That gives us 6 3 18 valence electrons. And we already have 4 from the various bonds, so that means that we have 14 left to redistribute. I'll put them on the oxygens first. 2, 4, 6, 8, 10, 12, 14. Okay, well, the sulfur only has 6 sort of valence electrons, so we can share these 2 maybe, so let's do that. Now the sulfur has 8. But what about formal charges? Well, let's see. This oxygen has 6 valence electrons minus 4 dots and 2 sticks. It's 0. Sulfur has 6 valence electrons. It has 2 dots and 3 sticks. So it has a formal charge of +1. And this oxygen will have a formal charge of -1 because the overall thing is neutral. The other resonance structure that you could have had, right, was you shared electrons from the right instead, so you'll have this setup. There we go. And with, again, sulfur having a +1 formal charge and this oxygen having a -1 formal charge. So these 2 are the resonance structures. Okay, what about the hybridization? Well, how many electrons groups do we have around the sulfur? 1, 2, 3. And the same for the one on the bottom, right? We have 1, 2, 3. Remember, double bonds count for 1 electron group. Lone pairs also count for an electron group. So we have 3 electron groups around the sulfur atom. So the hybridization of the sulfur atom is sp2 hybridized. Right, 3 electron groups according to our table above, all the way here, is sp2 hybridized, which means it's a trigonal planar structure, which means the fact that I draw it as a straight line is incorrect. It's actually a trigonal planar. So if I were to draw it properly, it would probably look like this, with the lone pair sticking out in this direction. So it's kind of a bent geometry, if you will. But that's the hybridization of of the sulfur atom. What about the bonds, sigma and pi? Well, we have 1 sigma bond here, 1 sigma bond here, and 1 pi bond there. So technically, we have 2 sigma bonds and 1 pi bond. Let's look at the hybridization. We know that the electronic structure for sulfur starts with neon, 3s, and then the 3p orbitals, and you'd fill this up with 6 valence electrons like that, but it's sp2 hybridized. So instead of this, we have 1s and 2p orbitals combining to give us an sp2 orbital, and then we have another p orbital left over, right? And then we have 1, 2, 3, 4, 5 electrons distributed like that. So what does this mean? We have 2 sp2 orbitals available for bonding, and 1 p orbital available for bonding. As we talked about earlier, these will help contribute to sigma bonds, and this will help contribute to pi bond. So we should be able to form 2 sigma bonds and 1 pi bond because those are the unpaired electrons. And then this set of electron here that's already paired up can't form a bond because it already has a partner. And so that set of electrons would be the lone pairs that you see on the sulfur. They're not available for bonding. So there we have it. Hybrid orbitals forming sigma and pi bonds again. I hope that all makes sense. If you have questions, please let me know. Okay, in some situations, when we form these sort of resonance structures, we can have what we call electron delocalization. Delocalization just simply means that the electrons, or pair of electrons usually, are not stuck on one atom or in one bond necessarily. So delocalization means the electrons are not stuck on a single atom or bond. So none of the examples that we've done so far shows that. Well, this one SO2 kind of shows that. For example, let's look at SO2 in more detail. So we have SO2, we said looks like this, and I'm going to draw the electrons around it. But we said that instead of sharing 2 electrons on the right, it could have shared 2 electrons on the left. So what if these electrons move in, then these electrons could move back out onto the oxygen, and so you have a setup where there's a double bond here, but a single bond here. Let me draw that second bond as a green one, because that's what we've been using. Right, and then we have our electrons that way. So we constantly have this situation where electrons are constantly moving from the atom to the bond, and from the bond to the atom, from the atom to the bond, from the bond to the atom. We talked about how we can draw a hybrid structure where we have a situation like this, where we draw like dots to represent the movement of electrons. This idea of electrons that are able to move from atoms to bonds, to atoms to bonds, those are called delocalized electrons. And they can only ever happen with pi electrons, electrons that are involved in pi bonding, right? The sigma bonds stay still. They don't go anywhere. They stay in the bond. But the pi electrons, sometimes they can move from one place to another. And let's look at a very common example of that, this idea of benzene. So here is the skeletal structure for benzene. These are all carbon atoms, right? 6 of them. And then sticking out from every one of the carbon atom is a hydrogen. And I'm going to let you complete the Lewis structure by drawing in double bonds so that you count for all the valence electrons. Pause the video and try to do it by yourself if you don't know yet. Okay, so to account for double bonds, we could have put the bonds here maybe, or there's an alternative option where we could put the double bonds. Let me just get there. This is an H. We could put the double bonds in the alternating position. But really, these, as you know, are hybrid structures where the double bond, let's use green, these pi electrons are constantly moving, jumping from bond to bond, right? I'm drawing here them jumping clockwise. They could jump in any direction, really, but they're constantly moving. And so those electrons are delocalized. All right, let's answer the question of what is the hybridization of all of the carbon atoms. Well, let's just pick any one of the carbon atom. Let's look at this one. There's 1, 2, 3 electron groups, no lone pairs. And so 3 electron groups, no lone pairs. We know what that is. It's sp2 hybridized. In fact, if you look at any of the atom, you'll see the same thing. 3 electron groups. Same for over here. So all of the carbon atoms are sp2 hybridized. Okay, how many sigma and pi bonds are in this structure? Well, let's count all of the single bonds. 1, 2, 3. Well, let me use yellow. 1, 2, 3, 4, 5, 6, 7, 8, 9 single bonds, and then the first bond in a double bond is also a sigma bond. So 9, 10, 11, 12. So 12 sigma bonds. What about the pi bonds? 1, 2, 3. 3 pi bonds. If you do the same with the structure over here, well, we should find the same thing. 12 sigma bonds, 3 pi bonds. Okay, try number 7 on your own, and then we'll go it over together. Draw the different resonance structures for carbonate ion, CO3 2-. Then draw a single structure showing the delocalized pi electrons. Now, if I were to draw a single structure representing these two molecules right here, what I would have, let's draw all the single bonds, the sigma bonds first. And then we said the pi bond could move from bond to bond, so we'll just draw a pi bond, sort of like this, as spread out over the entire ring of this molecule. Sometimes you'll see people draw it as a single circle in the middle instead of dots. But I like the dots, they look nicer. Okay, try number 7 on your own, pause the video, and then when you unpause, I'll go with you. Okay, for carbonate, we have 3 oxygens sticking out. How many valence electrons do we have? 4 from carbon, 6 from oxygen, and there's 3 of them, plus 2 from the negative charge. So we have 6 3 is 18, and 2 20, and 4 24. We have 3 bonds already, so minus 6. That leaves us with 18 electrons to distribute. So let's put them 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, this carbon has only 6 electrons. It needs 2 more. So it could borrow from the one on the top, the one on the left, the one on the right. So you can bet there are going to be 3 possibilities for resonance structures. So let me go draw the 3 possibilities. Let's make some space. So carbon, if it shares it from the top, will look like this. Carbon, if it shares it from the one on the left, would have a double bond there. And if it shares it from the one on the right, we'll have a double bond there. Always remember to draw your dots that are left over. There we go. Will take a while, but make sure your dots are correct and you don't put any extra dots anywhere. The one with single bonds, the oxygens, have 6 dots. The oxygens with double bonds have 4 because it's shared a pair. In all of these cases, the overall charge is -2-, so I like to put them in square brackets and put the charge up there so we know what we're dealing with. And we can look at formal charges if you want, by just sort of counting the valence electrons, and we'll see for these oxygens with single bonds, it has a -1 formal charge. And that's it. Okay, so these are the 3 different resonance structures that exist. Well, how many sigma and how many pi electrons do we have? Well, we have 1, 2, 3 sigma bonds, right? In all of them, so 3 sigma bonds and 1 pi bond. And now you can probably tell that the pi bonds move from atom to atom. So you can bet that there is sort of a delocalized set of pi electrons that can move from place to place. Well, let's see how it actually moves. Let's see how we get from the first structure here to the second structure. Well, what happens is one of these pair of electrons on this left atom, I'm trying to look for a good color. Let's do purple. One of these electrons sort of form a bond there, pushing these electrons up there. And so that's how you get this one being a double bond and now this one being a single bond with an extra pair of electrons on top. So that's how we go from the first structure to the second. What about the second to the third? Well, let's see. One of these pair of electrons push in to form a bond, and these bonds push out to go live on the oxygen out there. And then to go back to the first structure, right, what do we have? We have these electrons pushing in, that pushes out these electrons over there, to go back to what we had in the beginning. So these are the three different hybrid structures, and they show the movement of the pi electrons. Only the pi electrons move, the sigma electrons stay in place. So if you wanted to draw a single structure that sort of captures all of this, it might look something like this. Little dots there to represent that the electrons are sometimes there, sometimes not. The whole thing is 2 minus charge. All right, that'll bring us to the end of this section. In this section, just to reiterate, we basically did a combination of hybrid atomic orbitals and valence bond theory by looking at sigma and pi bonds as an overlap of hybrid orbitals and sometimes unhybridized orbitals. And we're able to count sigma and pi bonds in various molecules, and we also talked about electron delocalization. In our next video, we're going to look at molecular orbital theory. I'll see you then. Bye.